In this video, we are going to learn how to integrate using substitution. And so what you're going to notice in these problems is one part of the function that you're integrating is going to be a derivative of the other part. And so if you'll notice, if I took the derivative of this power right here, it would have some form of x to the fifth. So it would have a 12x to the fifth. And so this part is a derivative of part of that. So that is helpful because we're going to use substitution to make it easier to find our integral. And so basically, once you decide which part is a derivative of the other, you're going to use what we call a U-substitution and let U equal the, in this case, the highest power. So U is going to be the 2x to the 6 plus 3. Now, if we think about that, if we take the derivative of that of U in terms of x, we would get a 12x to the fifth, and then we say times the derivative of x, because we don't know what x is in terms of U. So now we're going to substitute back into the original function. And so notice we have an e, but in place of this 2x to the 6 plus 3, we're making our U substitution. And then you'll notice in place of the 12x to the fifth dx, we're just going to substitute the du, the derivative with respect to u. So now this is a lot easier to integrate because we know the integral of e to any power is just e to that power, and then plus your constant. Now when you're finished, you've got to make sure you go back to the final answer and put the u back in. So my u originally was 2x to the 6 plus 3, so I'm going to resubstitute that back in, and then I still have plus my constant. So that is called a u substitution. Okay, here's another example. Now, you don't directly see that one thing is a derivative of another, and let's rewrite this. So let's pull that cube root up to the top, so it would be a 3t minus 4, and when we pull it up to the top, normally it's a 1/3 power, but when we pull it up to the top, it becomes a negative 1/3 power. And if you were thinking in terms of that being a derivative, you've got to realize that you've got a chain rule involved. And anytime we've got a chain rule involved, we're going to have to use a u substitution to be able to go backwards and find out what that original function was. So in this case, you would let your u represent whatever it is that is being raised to some power that would involve me doing the chain rule. So I'm going to let that be 3t minus 4. Now you always have to look at the derivative with respect to u, and I failed to put my dt there, so let me add that back. And so when I derive this u with respect to t, I just get a 3, and then I say times dt. Now, it's not immediate when I go to try to substitute back in, so let me just kind of partially start. We've got a 5, and then in place of the 3t minus 4, we're putting a u. It is raised to a negative 1/3 power. All right, so the problem is we have a dt that we can replace, but down here we have a 3 dt. So what I always do is, if it doesn't go in directly like the previous example that we did, I solve it for whatever I have. So if I need dt by itself, then I would divide both sides by 3. So in place of my dt, I am plugging in du over 3. And so basically you can think of this 5 up here as 5 over 1, and you can think of this as a 1 over or 1 du over 3. So we could actually rewrite that as a 5/3, and then we have our u to the negative 1/3, and then we have our du. Okay, so we are now ready to integrate. I'm going to come down here as I do that. So the 5/3, I'm just going to carry along. Remember, rules of integration tell us that we're going to add 1 to the power. So when you add 1, that's like adding 3 over 3. So that becomes a u to the 2/3 power. And then we have to divide by that new power. So we divide it by 2/3. And then, of course, we always add our constant. Now, dealing with these fractions, dividing by 2/3 would be the same as multiplying by the reciprocal 3/2. That's what would actually cancel it off the bottom to bring it to the top. So you'll notice the 3's wipe each other out. So we're left with 5/2. And then we're going to put our u back in. So originally u was 3t minus 4. And then it's raised to the 2/3 power. And then we still have plus our constant. So that would be our final answer. And again, I'll stress at any time, you can then take the derivative or find the derivative of it, and it should match what you started with originally. And that's how you would know if you've done it correctly. Okay, so in this next example, what I quickly notice is that the y here is a form of the derivative of the power here. So my u value will be the negative 4y squared. It's typically your higher power. And so with that, the du would then become negative 8y, and then we would say times dy. So when we get ready to make our substitution in this case, we're finding the integral. So hang on for the 5y or actually we'll keep the 5. We'll hang on for the y just a minute. So we have a e, and we're raising it to the power of u based on our substitution. So basically, we still have a y and a dy up here. And when we look over here, we don't have just a y and a dy. We actually have a negative 8y dy. So again, I would go ahead and solve that so that we have just the y dy. And what that means is in place of the y dy, we're plugging in a du over negative 8. So again, if we want to clean that up, the negative 8 can come up here with the 5. So that would be a 5 over negative 8. And then e to the u du. So when we get ready to integrate, we still have our, I'm just going to call it negative 5/8. Doesn't matter where you put the negative. The integral of e to the u is just simply e to the u. And we always had plus a constant. And so for the final answer then, we would have our negative 5/8. We put our u back into the original problem, so that is negative 4y squared, and then you would have plus your constant. And then finally, last but not least, what I notice is if you look at this expression down here and you were to derive it, this x squared would be part of that derivative. So in this case, you would want your u to be the x cubed minus 7x plus 5. So then your du would become 3x squared minus 7, and that would be times dx. Okay, so when we get ready to plug in, obviously we have a u on bottom. Now the problem is we don't readily see this actually sitting up here. But if we come up here, notice the 12 and the 28, they have a factor of 4 in common. Actually, I'm going to take out the negative with it, negative 4 in common. And if we were to factor that out, that would leave us with a 3x squared minus 7. And then, of course, you have the dx. So the negative 4 is part of the original problem. In place of this, notice we're just putting in the du. So we've made our substitutions. We are ready to integrate, so the negative 4 is just a constant we carry along. Now, you can think of this as, in fact, if you wanted, you could pull the negative 4 out to the front. So we're really just integrating the 1 over u times the du, and that's where we talked in an earlier video, the integral of 1 over u is going to be the natural log of the absolute value of u. You have to keep those absolute value bars around that. And then plus your constant. So for my final answer, if I put my u back into the original problem, my u was x cubed minus 7x plus 5. And then, of course, I have my plus my constant.